This is our fourth video on finding the electric field due to various charge distributions. What we're doing is we're finding the electric field due to non-point charge distributions. What we have here is a non-uniform rod, and we want to find the electric field at this point P. First of all, it's going to point straight to the left, and that's because electric field lines point away from positive charges. And we can see by the drawing here that this is a positive charge. So the electric field at that point is going to point straight to the left. It says here that this is the first time that we're meeting lambda, which is linear charge density. So lambda is charge per length. And that means that the unit for lambda is going to be coulombs in the numerator, meters in the denominator, coulombs per meter. So what we're saying here with this is that the density of the charge is not constant throughout the whole length of this rod. Previously, we have met situations where the charge per length is a constant, and that's not the case here. You can see by the equation above the rod that the charge density increases linearly as we move further and further to the right. On the left end of this rod, the charge density has a value of some constant, alpha times A, and at the right end, the charge density is greater. It's going to be equal to alpha multiplied by the quantity A plus L. What we're going to have to do is we're going to have to imagine that we break this rod into a bunch of tiny little DQs, each of which is a distance r away from our point P. And that tiny DQ, much tinier than I'm able to draw, has a very tiny thickness, which I'm going to call dr. So here's what we'll do. The total electric field at point P is going to be equal to the sum of all the little dEs due to all these little dQs that are a part of this rod. We've talked in the past that the electric field for a point charge is equal to kq over r squared. So to find a dE, we're going to go k dq divided by r squared. And as you can see from the picture, we need to integrate this from a value of r equals a to a value of r equals a plus L. The problem we're running into now is that the limits of integration are in terms of a length. That's a unit basically of meters, but our differential is of charge, and that is a problem. So we need to essentially somehow change this dq into some kind of dr. So how do we do that? Well, let's look at this little dq that we've put in our drawing here, and that tiny little amount of charge should be equal to the charge density at that specific point multiplied by that tiny thickness. Fortunately, we're given the value of the charge density at that point. It's given in that equation. So what dq is equal to? It's equal to some constant alpha multiplied by r times dr. That then is going to get substituted in here for dq. And now our differential and the limits of our integration are going to have the same units, and they'll be, you might say, speaking the same language. So let's integrate this from r equals a to r equals a plus L, and let's substitute things in. K multiplied by alpha times r times dr, that's the numerator. The denominator will be r squared. One of the r's cancels, and that leaves us with k times alpha divided by r multiplied by dr. Now, k and alpha are constants, and that leaves us merely to integrate dr over r. And the integral of dr over r is the natural log of r. So we're going to end up here with k times alpha, the natural log of r, as the limits go from a to a plus l. And since any logarithm, the subtraction and the division give you, in effect, the same answer, I think we can simplify our final answer to look like k times alpha times the natural log of a plus l over a.